Okay, so let's get back to the course, the class today. So the first thing is we're going to talk about the thing that we are actually trying to model. All right, the sort of the goal we're trying to understand. What is it that we're trying to understand? And the thing that we're trying to understand are actually biological neural networks. We're not interested, as I said, not really interested in so-called understanding how ChatGPT works or how LLM, as we see in commercial apps. We're not interested in how they work or how they are applied. We are interested in how we see the fact that we have brains, or animals have neural circuits, and they are wired together, and they are biological in nature. And in their operation, they give rise to, we observe, behavior, right, and activities. And so we are interested in understanding what that means. How does that work? Okay, so this has to take the first primary picture and reminder here. This page is a work in progress. Personally, I think it's a mess. Because I started this last year. This year I updated a little bit, and I'm probably gonna update it some more, all right? But so, don't worry about it. Don't take it too seriously. But it's just a tool for me to remind me of what I want to say, all right? So, and I think all of you probably already know this, right? The fact is that when we talk about neural networks, what are we talking about? We have a neuron consists of basically you have the cell body, the neural body itself, okay? And this neural body, this cell body receives input, so you got arrows going in, okay? From other neural bodies, from other neurons, okay? And the input comes in from synapse, okay? And they are from the dendrites, and on the dendrites there are synapses. And then it sends outputs, okay, through axons to other neurons and terminates on the other neuron also via synapse. So if we put it together, you have different neurons. There's an example of 4 neurons here, and they are simplistically connected to each other or to other neurons outside of this network, and they receive input from other neurons outside of this network, okay? Just this picture here, conceptually, I think everyone knows that. And what we are talking about, we have to know that this is obviously wrong, okay? Because it is not true that a neuron only sends one connection to another neuron. A neuron, when it connects to another neuron, might have very complicated kind of structure, right? And also, it may be that it's not so simple, like it just receives from others and then it just sends out kind of almost passively. There's probably a lot more other kinds of connections going on. But even with just this idea, it's already quite complicated. So we will keep ourselves simple in order to be able to manage what we are going to code for this course, at least, okay? Now, then, beyond knowing that it's basically about different nodes of neurons connecting to other neurons, we should know that basically what we mean by connection is, as we said just now, is about synapse. And what happens at the synapse is that you've got these neurotransmitter molecules that when the presynaptic membrane gets stimulated, it causes these neurotransmitter molecules to be, well, they are encapsulated in vesicles, and then they are bound to the membrane, and then they are released, okay? Procedure is like this, right? So, excuse me. So you've got all these molecules in the presynaptic side, okay? They are first prepped and ready, and then when you get some axon, the action potential comes in, it causes these vesicles to bind to the membrane, the presynaptic membrane, and then because they're bound, they open up, and then they release all these molecules in the synaptic cleft. And when the molecules are there, they bind then to the receptor on the dendrite of the next neuron, okay? And because when they bind, they cause changes in the membrane potential again. If you get enough of this binding, the membrane potential builds up, and then that leads to the signal in the next neuron. This is very simplistic, okay? There are many, many other complex operations going on. Essentially, this is still our current understanding, okay? Then, what happens to all these molecules that are floating there in the neural synaptic membrane? Well, they get reuptake, they get sucked back up, okay, through open channels, okay? Or they degrade, or they might get even sucked back in the postsynaptic. There are many operations, but they have to be cleared. Otherwise, the membrane is still active and the voltage is not going to change, right? So this very, very complex, a lot of action happening here, okay, to make it so that when you get an electrical signal to the synapse, it translates to a chemical signal that then induces another electrical signal in the next membrane. And these chemical components have to be kind of recycled or reused or modulated so that the next electrical signal can come, leading to chemical signals, leading to more electrical signals. So this cycle has to keep happening over and over and over again. And it's all supposed to happen in sub-millisecond. It's faster than 1 millisecond because one action potential already can be in milliseconds. So which means that all these chemical things are happening at sub-millisecond time resolution. Very, very fast. Okay? The translation and the stimulation and then the reset, sort of going back to baseline. Okay? So there's a lot of detail here. You don't really have to know it, but essentially what we have is like until we get enough build-up, so up to this point where we get a stimulus, okay? If the stimulation for a neuron, okay, at the postsynaptic membrane might build up some potential. So more and more neurotransmitter binding to the dendrites, okay, it will change the potential of the membrane a little bit, but if it is not enough, if it's just a few, then it's not going to lead to the next neuron firing, okay? But only when, let's say, you reach a certain threshold, okay, then it will lead to a sudden kind of like the floodgates open and then the action potential gets transmitted. And then after that, it has to have a refractory period and then it goes back to rest. Okay, so that's essentially, very simply, what we're talking about here when we talk about all these things that are happening at the neural network. And this is biological. This is real in the sense that we see this is how it happens in the brain. This is how it happens in every animal that has a neural system, okay? This is how neurons work. And this is been super summarized, okay, when we say we model it and when we say we apply it to artificial intelligence, we have basically changed it so that, it becomes this node, connects to this node, and then there is an activation function, and we'll talk more about that later. And all of those other levels of like, the neurotransmitter is released and they have to be reuptake and all that, it's kind of like not in the picture at the moment. Okay? So, let me clarify. When we talk about neural network modeling, that's what we're talking about. We're talking about this very highly summarized, kind of like we have nodes connected to other nodes, and then they have some activation function relating each other. That's what we are worried about, okay? To be fair, there are biological computational modelists where they will care. They will care about these things. So for example, they care very much about this function here, okay? The Goldman-Nernst equation, right? You don't have to worry about that, okay? What this is basically saying like, well, what is the resting potential of the membrane? It's minus 80 microvolts. Then they care about like, so how many channels are there, and like when you get, and if you guys know, it is about the sodium, potassium ions crossing the membranes, right? And then causing the charge to either increase or decrease, right? So they care how many ions are going in, how many ions are coming out. So how much charge is going in, how much charge is coming. They can model it things all the way until this level of precision, okay, at the molecular level, at the electron level even, okay, and they're concerned about the shape, the exact shape of this, okay. There are people, computational biologists, who are working on that. That's not the same as neural network modeling, because neural network modeling sort of summarizes all these and then just says, well, it's just either on or off, almost binary level, okay? And it depends on whether this one is on or that one is on, you know, who is on or off, then we get some kind of a very dynamic state thing, okay? So this is to first introduce the fact that yes, we are interested in the biology, but the biology has different levels in itself. You can be concerned about the biology at the level of those molecules and the biological like substrate, or you can be concerned about the biology in the sense of that, well, what we observe at this, what I would call the meso level of structure, which is kind of like the middle level, not the molecular level, but the kind of structural object level of a neuron and how they are connected to each other. That is a biological neural network, okay? If you were to go deeper, like I said, the computational biologists, then we will call that more like molecular modeling, biomolecular modeling, okay? We are not doing biomolecular modeling, we're modeling things at the network or system, small system level, and actually even at the big system level as well, all right? But it's biological because the danger is this, because we are operating at this level, at the system level and the node to node level, okay, it is easy to forget that these nodes don't just do anything that you want it to do. Anything that's mathematical, you can do it, okay? That's not true, all right? It is still constrained by biology. So biology doesn't do funky stuff, and we can talk about that when we come to it in terms of activation functions. Biology doesn't do like weird activation functions. So biology does this as an example. Biology does where if you add thresholds up to a certain point and you don't cross that threshold, it doesn't activate. But when you cross the threshold, suddenly it activates. So it's almost binary, okay, in that sense. So biology does that. But mathematically, you can imagine, I don't have to do that. I can do like small, I activate, middle, I don't activate, only high, I activate, or some other complex weird thing. And I don't activate in just a one pulse. I activate with a sine wave or something like that. Engineering-wise, you can do that for sure. Mathematics, you can do that, all right? But biology doesn't do that, okay? So that's what I mean. So we have to be aware that when we do all these modeling, actually mathematically you can do anything, all right? But is it what the biology is doing, okay? So that again is in distinction to, let's say, an engineering problem. Engineering problem, maybe this is inefficient. Why do I just want to do things biologically? Binary. Why don't I do it as a float value, you know, different levels code for different things, right? And then you find that, hey, it solves problem even more efficiently, right? Okay, you can go that route, but no, here we are constraining ourselves to say, well, but biology does it this way. So let's try to understand how biology does that, okay? All right, and another thing I want to bring out from this illustration is this. So the student asked questions just now, right? So yes, this is a graph. This is a computational graph, okay? And if you read the Agarwal chapter, you will realize, and I kind of hinted it just now, everything is a computational graph, okay? Everything can be sort of construed as a node state leading to another node state, and their relationship is the edges, the arrows, how they are related, right? So for example, this node cannot influence this node directly because there is no edge here. Okay, but this node can influence this node directly, and so this node can also influence this node directly, and their joint influence results in that the secondary node having some kind of response according to the relationship, according to whether this node is a strong one or a weak one, or whether this this edge is a strong one or a weak one, or this edge is a strong one or a weak one. I'm sorry if I skipped something. Maybe some people aren't familiar with graph theory, okay? But we call these nodes and we call these edges, okay? Or you can call it like nodes and connections if you want, or weights or weightings. In fact, neural network, we will call them weights. We won't call them edges, okay? And sometimes you call them vertices, Okay, not nodes, but vertices. Okay, you can call them that as well, vertices and edges. It's all the same thing. It's about the idea that you have a circle and then a line, and then the circles are connected to each other by these lines. Okay, all right? And so obviously also, like, you get this node doesn't feed back to this node because there's no line here, no edge here, but you can if you want to design your architecture that way, all right? But so this essentially is that when you have such a representation, okay, a graph representation, then it is about whether this is on or off, or how active it is, and then how this being on or off, or its activation state, how it is related to the activation state of another node. And once you have that fundamental, it's essentially a graph, a computational graph. How I influence my neighbor, how my neighbor influences me. Do I have influence over this neighbor or not? Or like, no, we're just independent or not. Okay? Any problem, as long as you construe it that way, it's a graph problem. It's a graph theory, computational graph problem. And so that's essentially what we're dealing with. Biological neural networks are computational graphs with biological constraints. Okay? All right? Easy, right? I don't think it's hard to understand. It's very intuitive. Actually, neural networks is very simple. It's just, you know, because the biology is doing things actually in, as complex as it is, its base operation is actually supposedly very simple. All right? It's just that it's been added up into a complex way, that's all. Okay, so then the next thing, any questions about this? Anything to add? No? Yeah. All right, so then now let's go to the a bit more abstract. Okay, so if we accept that that's what's happening, that what we are dealing with is all these nodes and edges, computational graphs that have biological constraints, let's break that problem up into its components. And this is what we will be doing a lot in the subsequent courses. Okay, so let me state that the key aim basically is, so how do we know how it works? What is the process by which we we want to form a network to sort of test a biological neuron, how we think a biological neural network is working, right? So what is the procedure or framework we use? So first we have to define the problem. Okay, the problem set, the structure of it. And this is a proposed way of defining it. That definition is first, well, when we want to create a model and evaluate the neural network model, essentially what we mean by that is that when I have some input, okay, that's called the input AI. Let A subscript I, okay, not artificial intelligence, just A and I. And let's say this AI is the input. So what we mean by input is, let's do it very concrete. There's a flashing light, or there's no flashing light. Okay? So let AI be 1 when there's flashing light, or 0 when there's no flashing light. Okay? So that's the input, whether there is light or no light. And that is what AI represents. Okay? Now, this AI goes into this neural network system, this computational graph. We call it X, okay? And then X, because of how it's made, gives rise to some output AJ. So for example, it will press a button, or it doesn't press the button. Okay? Very simple, right? There's a light, go into the X do something, and AJ comes out. No light goes into the X. Okay, no light is also another stimulation, so to speak, right? Negative stimulation is a stimulation of sorts, okay? And it goes into the X, and then, oh, don't press a button, okay? Very simple, right? So AI goes into X and gives rise to AJ. And we are trying to understand this. Sounds very simple, but even trying to understand this is a big, big, big problem, okay? That's the heart of it. So then, well, let's formalize things a little bit more. So we have AI, and AI, let's say, as I said, can take 2 possible states. So, so part of this course is also like, I'm not just trying to teach you things conceptually, but conceptually, how do we express it formally? How do you write it out as an equation like this, okay? Or some formal terms like this. So for example, we can imagine that if we accept AI is about the light on or light off or some input states, then we can say, well, AI has at least two states, AI1 and AI2. Okay? Let's say AI1 can be represented by this string of 4 numbers. We call this a vector, a 4-dimensional vector, 1010, or a 4-bit word if you want. And this can be anything, okay? So if I say 1010 means the light is on, okay? And then 1100 means the light is off, okay? Or I can say 1010 means cat and 1100 means dog. It's arbitrary what it really means, but when we think about it in our abstract conceptual domain, we can think of things like this, okay? Let me make it even more concrete. Let's go back to the light example, okay? Why is it a 4-bit word? What does it map onto biologically? Okay, if we take our retina, okay, our retina, let's say, has millions. In fact, I think we have 2 million, they're estimated 2 billion retinal cells, 2 billion retinal cells, so 4 billion in both eyes, okay? We'll talk about that maybe another course, but another class. You can actually go and count how many sensory cells you have on an average human body. So that means AI will be that n-dimensional vector. It's in the order of billions, right? We have billions of sensory cells. So AI is a 1 by however many billion vector size, okay? That's going to be squashed into the X, okay? We'll come back to that. It's very intriguing, and I've been playing with that idea recently. But okay, but let's go back to, this is just a 4-bit word. So if we translate it to, let's say that this is a retina that sees whether there's light or not. Let's say a 4-bit word is just about the position of the light. Is it up, down, left, or right? So there's only 4 possible states. It's either up, left is on or off, up, right is on or off, bottom left, bottom right, on or off, okay? So what this means would be, if I want to say up, left, right, bottom left, right, will be this left side, 1010 means left side is on, right side is off, okay? And then the next thing that happened is this display, the upper row is on, and the bottom row is off, 1100, okay? That's what it means. So I can make the input kind of anything I want, but I just convert it, translate it into a binary n-bit word, in this case a 4-bit word, and I can use it to mean that I have 4 channels, and each of these channels can have different on or off states. And because of that, I can create 2 possible or more possible states of inputs. Okay? You can calculate how many possible states of inputs here very easily, right? So it's a 4 square, however you calculate the number of combinations. So you put all these 2 possible sets of inputs, and then you feed it into my network, and then it gives me an output. Let's talk about the output. What could the output be? Pressing a button is 1000, okay? At least pressing my index finger. Let's say I have 4 bits, right? Okay, so 4 fingers. So let's say if I have 1010 or 1100, that means I press my index, okay? But let's say I change the binary input, maybe then I'll press my middle finger, maybe I'll press my other finger, or I can press 2 fingers, or I can press no fingers, okay? So that's what the 4 output channel could mean, okay? Any questions? Simple, right? So far, very, very, but see, what we have done is we have taken an everyday, very biological, very natural thing we take for granted, sort of, and we have kind of formalized it into a mathematical, formal expression. It's very powerful because when you can play with this in this domain, then it leads to some implication in real life. So for example, if we understand how X works, then I can predict if I give you 1001, what's your output going to be, let's say, given the X, whatever X is, okay? That's the problem at heart. So now, and so that what we see here basically is that the fact that it's like, if I read here, okay, dynamical applications are sets of problems where the results of a function depends on previous results. Why this, as we have framed it, is a challenge is because how X works, okay, is not so easy, right? Although we have made it so easy, like, okay, you give some input and give some output, right? You can think about it like, okay, if it's linear, if it's simple, then I can totally, I just give you A, you will definitely give me B. I can always predict that, all right? It turns out that it's not so simple. And it's because X, the way X works, is dynamical. And dynamical means that they, at any one time, AT, let's say, and I would say AJ first, okay? Let's make AJ equals to AT. What AT is depends on what AT was before. So in other words, whether I press this button now not only depends on the input I see, it's not so simple, it depends on whether I press the button just now or in the past before. So that is part of the function that governs, this F here is a function, okay, that takes what was happening before and puts it into a proportion of what is going to happen now, okay? So in other words, our brain, our X, is not like I just see a light and then definitely I will press it. My brain works in a way that when I see a light, I might press it, high probability I will press it because I've pressed it before, because someone else told me to press it. But maybe I remember, wait, I'm tired, and I don't press it. My brain can totally do that. And that will mess up the equation, right? That will mess up this in, X, out kind of thing. Because who knew that some other in or some other state could change the way you relate the in to out? And most of us will think of it as noise. You think it's error, random noise. It's not. It is part of your computation of X that determine why you decided to do AJ and not some other AJ. Okay? And that is the nature of a dynamical system in the sense that when this current state actually is not just based on some objective or arbitrary function on its own, but it is also based and constrained by its own previous state. Okay? This is what we call a dynamical function. And if those of you who are interested, you can look up dynamical equations. It's a whole field of research on its own. Okay? And it is in the field of dynamical systems and chaotic systems. Okay? Chaotic systems means that the chaos functions are that I cannot predict what's going to happen later accurately. I can roughly predict it, but in order for me to figure out exactly what's going to happen, I actually need to let the equation play out. Depending on how you start, you will end up in different places. Okay? So that is the formalization, okay, and the key challenge. We want to know how X works, and it would seem that how X works can be simply expressed like this. Unfortunately, X works dynamically so that we have to play it out. We can't just write some math and then predict, oh, that's exactly how X works. We have to try and say, we think X works like this, and then we have to play it out. So in other words, that's why we have to do simulations. And then we see that most of the time X works like this. Okay? All right, so that is the sort of where we're at right now. Okay, so let's keep on that. So how do we do that? Well, first thing is, well, we want to know how X works, right? So then we propose the fact that X is going to be made up of a kind of a matrix of weights. Like I said, you have two nodes and the weights are connecting to each other, okay? And the activity of the output node is going to be equals to some function, okay, of the sum of all the weights modulate, all the input modulated by the weights, okay? This is the core activation function. Okay, and you read that where W are the weights that scale the summative contribution of the nodes AI, the input, on AJ, in other words, the connection weight. So graphically speaking, the output is going to be equals to AI1 times WI I1J, okay, plus AI2 times WI2J, okay, and some function of it, okay. It's not just like this times this plus this times this gives you AJ. No, it's this times this plus this times this, okay. That sum, you pass it through some function, and then that gives you AJ. There's another kind of a filter going on here, all right. And since we're here, let me highlight to you, in this class, I will try to consistently use I meaning input, J meaning the output, or it could be I is the previous state and J is the next state, okay? And when I say Wij, I mean the input to the preceding side and the subsequent side. So Ij means the edge or the weight is from the direction of I to J. I can also do Ji, which means that the weights is this direction, the reverse direction. Okay? So the order matters, okay? And the subscript here, I1 or I2 means that at the layer, at the ith layer, the ith input layer, there are two nodes, AI1 and AI2. I can also have at the jth layer, the output layer, here I only have one output, but I can have also AJ1, AJ2, etc. Okay, so this is the notation I'm going to use. So for example, if I have two nodes, AJ1 and AJ2, then I can have a weights from WI1 to J2 as well, correct? Okay, and when I use capital letters, uppercase, it means I'm talking about the matrix of all the weights. Whereas if I use lowercase, I'm talking about one particular instance of the weights, okay? I will talk more about that in subsequent classes, but this is just by way of an introduction. Okay, any questions so far? Okay, so here is where we've been talking about biology and the concepts, but now we're going into the sort of the formal math of it, and we need that, okay, in order to run our, create our models. All right, so I talked about that. Well, it is a sum of the input multiplied by the weights, okay, that somehow leads to the output, and it is always put in the, within an activation function. It is true that one function could be the sum itself is the output, okay? That is a function. The function is that it is equals to that, right? But I can also do such that if the sum is greater than some number, theta, then make that Aj equals to 1. But if the sum is less than or equals to theta, then make Aj equals to 0. So this itself is another function, okay? So it's not exactly the sum, it is the sum if it is greater than some constant, let's call the constant theta, okay, a threshold, then the output is just 1. And if the constant, if the sum is less than or equals to the constant, then the output is 0, okay? We will revisit this in subsequent lectures again, but this is again to introduce to you the concept that you have sum of weighted products, okay, but it passes through an activation function, and a possible activation function is this one, which is a binarizing function, okay, according to a threshold. And then another possibility is this function, okay, so Aj could be equals to 1 over 1 plus e to the sum, to the exponential of the weighted products. Okay, if those of you who recognize, this is the sigmoid S shape. Okay, I won't, Nick, do I have, I guess I can draw it out just to show you. Give me a second here. Yeah, okay, good. All right. So if I do this works. AI, nope. I'm going to use a bit smaller. Okay. AJ is equals to the sum of W AI. Okay. Then if I were to plot it out, why does it do that? Then it will look like this. Right? As the sum of the weighted products increase, AJ linearly increases. Okay? If I were to do this, okay, some exponent of it, basically, the rest are constants. Then the equation, the relationship looks like this. Oh, sorry. I believe there should be a theta there, correct? Yeah. This is theta, okay? And there'll be a theta here, okay? And the line will look, let's change it so that it's red. And I believe this should be 0.5 based on this equation. Okay? So if this is function 1, that means that there's a linear relationship between those inputs and the output. If it's function 2, then I've changed the relationship. So it's not linear, but it is some sort of a smoother S-shaped thing, okay? And then if we go to the one I said just now, where it's equals to 1 or 0, if okay, if it is F3, then it looks like this. You can imagine it. Think about it. Okay. What do you think it will look like? That's why it's fun, because you can see the equation and then you can imagine what it will look like in your head. It will look like this. Right? Okay? Okay. So I do have a last, so these are the 3 functions. There are many possible functions, okay? But those are 3 quite common ones, a linear one, a sigmoid one, and what we just call a rectilinear one, okay? And I have, if you go back to the notes there, so if I go back here, let's see, this should be the PC. And this one should go back here as well. So if you go back to the notes, the last function there is this one, okay, where it's a very complicated thing. It is, the output is a ratio of a given input sum over all sums of all sums input. Okay, this is a softmax function. Okay, where the output is the ratio of the input coming from one neuron as a ratio of all the inputs coming from all the other neurons. Okay, that's what this equation does. We won't spend too much time into this mathematics, okay? Just to introduce, you see, things can get pretty complicated, okay? All right? Okay, but they are nonlinear. If you use a sigmoid or a rectilinear function, it's nonlinear, okay? It's not a straight line. Okay, so we have this activation function which determines how an output is related to its inputs. Okay, so this is the activation function. And then we also have a learning rule part, okay, where because the way a neural network works is, as we said, it is not linear, it's not linearly determined, it's dynamical. How it responds now depends on how it responded before, okay? And this is instantiated also by the learning rule. For example, there is a learning rule such that you can have a learning rule such that the weights of ij depends or is equal to the sum of the input and the output according to this relationship. Okay? If you see here, this is, and we will learn this in the hot field network. Okay? If you work this out, and let's limit AI and AJ to be binary. They can only be 1 or 0, okay? So if I switch back again to the whiteboard, okay? So if we imagine that, then we have a learning rule such that, Wij is equals to I don't need a sum here, but let's just play this out. Okay, let's say this is the learning rule. Okay, so and let's limit that AI and AJ can only be binary, so there can only be this kind of situation, right? They can only take 1 or 0. So in terms of this, there's only these 4 possible combinations. And the logic table tells you that if you give this one, I believe it is +1, -1, -1, +1. Correct? Work it out. Okay? When AI and AJ are both 1, Wij will be +1. When AI and AJ are both 0, Wij is also 1. But as long as one is not the same as the other, Wij will be -1. And if you make it such that the weight will be, and if we say change in weight, okay? If the input is the same, and input and output are the same, then strengthen the weight, +1 the weight. Right? And same meaning, it can be both be active or both be inactive. Okay? If that's the case, as long as they're the same, add 1 to the weight. All right? And if they are not, if they are, one of them is different from the other, then reduce the weight, suppress it. Okay? So imagine, I had the case where okay, so if I paint that picture out to you, these two will be at first random numbers. Okay, at first maybe this and this are random numbers, but if this is the same, then this means I will add 1 to it. If this is different, then it means I will -1 to it. And I keep doing it over and over. So it will +1, -1, +1, -1, +1, +1. You know, depending on how the dynamics play out. So it's dynamical. Okay, so this is a simple introduction to a learning rule. Learning rule meaning how I update the weights. Okay, and don't worry, we'll also revisit this in the future. Okay, so let me go back here. Okay, so we have these two components of we define an activation function, we propose an activation function, and then we also define a learning rule. Okay, this is two components of how we approach the problem. We define an architecture, how the nodes are connected. Okay, we define an activation function, which is it like binary, is it a smooth sigmoid, is it a linear or whatever. Okay, and we define a learning function, how the weights change as a function of the previous weights, as a function of the input-output activity. Okay, these three components, these three operations, okay, will help us to solve, or at least is the way we use, is the kind of concept we use to solve how X works. Okay, when X receives input and gives output, how X works. We first propose X architecture. How is it 2 nodes to 1 node, or 3 nodes to 1 node, or many nodes to many nodes? How are these nodes related to each other? Is it a sigmoid? Is it linear or whatever? And how are the weights themselves changing with respect to the activity of the nodes and previous weights, etc. Okay? So we have, again, broken down this biological system kind of notion into very concrete, formal, and operational kind of understanding. And we will use this to define our architecture, to define our activation functions, to define our learning functions, and then we will simulate it. We will evaluate whether our architecture, our activation function, our learning function, whether they make the network do what we think it's supposed to do. Then we run simulations. And so that is this last part, which is that we will run simulations to assess and evaluate the neural networks. Okay? And for example, how do we use a simulation? What does a simulation, how do we do it? Well, for example, given that we have some weights or activity, okay, that network is going to have some energy. We call it energy. This, for example, we might define energy as this minus half product of weights and activity. This is actually kinetic, a form of kinetic energy, okay? And what it means is that if my network is working efficiently, then maybe my expectation is that the energy should be low. It shouldn't be like working very hard. With respect to the input and output, right? The input and output should be like very much together, so there's not much perturbation going on. Okay? So the energy is low. If the input and output are always disagreeing, then the energy is quite high. Okay? Which suggests that my network is not really working very well or very efficiently. Okay? This is one metric. There are many other ways of evaluating, but for example, we can use energy. And this is for the simulation, the neural network. We can go to the brain. Is your brain, if you were to look at all its activity, is it very active or is it very quiet? When the brain is very active, if you measure it using, let's say, fMRI, you use Bose signal. Bose signal is a reflection of oxygen and metabolism. You can measure it using electrical pulses. If there's a lot of electrical pulses, it's obviously very active, as opposed to it's not firing at all, it's very quiet. You can use calcium. Calcium means that it is receiving signals and doing some computation, right? It is all very lighting up, so it's very active. Or no, it's very quiet, very dark, okay? So it's energy. All these are energy signals. If the network biologically is working very hard, then there is high energy signal. If it is not working at all or very quiet, then it has low energy signal. Similarly, in a simulation, if we get things right also, we can match, hey, whether the two energy profiles are similar or not. So that's one of the ways we assess and evaluate neural networks, okay? And there are other ways. For example, we will talk about Hamming distance, and we'll talk about how long it takes to settle. All these are embedded. If you run a code and you get an output, if the outputs are the same, then the Hamming distance is very small. If the outputs are very different, then the Hamming distance is very far apart. If it is very efficient, it will settle very fast, a few iterations. If it requires, it keeps running and doesn't settle, for example, okay, then there's a problem, right? Okay. All right. So that's the sort of general framework that we will use. We will have architecture, activation function, weights, updating, learning rule, and then we assess and evaluate our simulations using, again, various different methods or functions. And the whole idea really, all of this needs to be constrained in the idea of neural plausibility, at least in this course. If you're in an engineering course, this statement can be cancelled out, okay? But in this course, what we want is to see whether what we simulate and what we are doing is neurally plausible. Do we have an example of it in the brain? Do we have an example of it in some neural tissue or some real-life example, okay? It's plausible if we see these kinds of, the way we make the architecture seems to look like how we know the brain is connected. The activation function we choose, the sigmoid, seems to be like the action potential, like up to a point, then it fires, and up below a certain point, it doesn't fire. Okay, so that's neurally plausible. And then when we have a learning rule, like it's like if they are similar, then they increase the connection, right? That's the Hebbian rule. Hebbian rule, fire together, wire together, right? So again, that's neurally plausible. Okay, out of the many possible architectures, the many possible activation and learning functions we can use, not all of them are neurally plausible, only some. So we have to constrain all these kind of structure that we build into our model. They have to be neurally plausible in this class, okay? They don't have to be if you go to another class, all right? Okay, so yeah, all right, so that's next one will be for next week already. But so this week, for this class, this is the brief intro and kind of guideline of what we hope to do and the way we will do it, okay? And the kinds of ways of thinking. And I hope you appreciate it. It's about like, we observe reality, we observe biology, we observe behavior, we observe psychological kind of phenomena. We have memory, we have attention, we have decisions, we have emotions, things like that, right? Psychological things and behaviors. And we translate it to some sort of formal mathematical, kind of representation. And then in that domain, we really are critical about what we mean when we say it has memory, what we mean when we say it sees some percept and then makes an action. It must make sense mathematically. And when we talk about mathematics, anything is possible in mathematics, but only the class that is neurally, biologically constrained and possible. That's what we talk about, okay? And then those parts, how we do that, which is about those functions and how we define those classes of operations that we do. So this is the course. The course will be doing this over and over and over again, but using maybe different examples of phenomena, psychological phenomena, and different kinds of functions that we see kind of make sense neurally, okay? And then we play with it, we see how it works, and then hopefully at the end of 16 weeks, you have learned something more about neural networks, as opposed to what they tell you on the internet that, oh, is this LLM, and just give this big data and then I can do amazing stuff. You have no idea what it's doing, okay? This one is kind of, you should be crystal clear about where the numbers are coming from, why this number is high or low or that kind of stuff. This is how we want to inspire you guys to think that way, okay? All right, any questions about all of that today? Yeah. ReLU, yes, regularized linear unit, correct. Good question. We'll talk about it later, but if you want to know about what a ReLU looks like, it's like this. Okay, all right. ReLU, we will talk about it when we get to that Agarwal first chapter, but ReLU would be looks like this. Okay, and you can think about it. This line, how do you express it mathematically? So when it's less than theta, okay, can put less than or equal, okay, right? So, and then, okay, what is when it's greater than theta? So slope is 1. In this case, let's say the slope is 1. So what do we fill in here? Can you guess? The timer? You can. If the slope is, yeah. So, 所以 AJ as yeah 对抓到了，所以是这样。Right? Okay, so it's different from the other one where we had it such that it's I think yeah. Right? This one. The red line. Oh. Right, can go to infinity at the moment. At the moment, I mean, 你可以自己 define your function, 好 but basic ReLU, 因为他们也有很多 ReLU, okay? But this is basically what ReLU means. Regularized linear unit. It is regularized because at some point it's not linear, okay? This is the part where it's not linear. There's a kink in the function. But after that, it's linear. So it's been regularized. It's a linear thing, okay, because there's that linear component, but it has been regularized by a nonlinear constraint. Yes? 什么？再大声一点。啊 ，AJ 要减到西塔，可以，对，你可以减 theta 也是。there are many kind， 你可以说那个 weights，那个 AJ 可以减 theta， 就是 to normalize it or to regularize it 也是可以这样子，没错。if you want, you can do a code. I guess we'll talk about this next week. I think. Oh, sorry. Let me go back and find the code. But there'll be some, I think it's sine WAI minus theta, something like that. Okay, let me go back and find, I have it, I can't think of it right now. Okay, but if you run it in a computer program, how do you implement this? 就是 you can do it as an if-then statement. If 这个大于什么 then you do this. If 低于什么 then you do this. Or you can do it in one line. 就是 just choose the maximum of the two options 就可以了 right? Yeah. 然后 in that case 就是有一个减 t theta 的那个在里面 some sort of thinking about it. Same mathematically is the same. Yep. Okay? Any other questions? I'll clarify this the next class. We will talk about it for sure in the next lecture when we talk about Agarwal. Okay, ma? Okay. Is this too tough? Is this too difficult for now? Okay. Well, it might get tougher, but I mean, I think the idea is this is where we're at. We're trying to get it so that we can figure out how to translate from one world to another world, and then to see how it works. Okay, so this is about as intimidating as we want to be in terms of the math and what it means. Okay, we will just keep it at this level. All right, so if not, then let's call it a day. We just have 10 minutes to end class anyway. And if you guys have any other questions, you can, I'll be here for a few minutes, but then, or you can email me, and then if not, then I'll see you in 2 weeks' time. And hopefully you will spend the time to read on the initial materials that I just said and kind of brush up on your linear algebra and your coding. And if you have questions about registration, or if you meet issues and all that, I don't know how things will play out before 3rd of March, but if there are, just do let me know, okay? Yeah, so you should have my email contact, so just go ahead and send me a message. All right, so that's it for today. Thank you very much. I'll see you in 2 weeks' time. And then stop this one. Okay.